All right. Hi, everyone. My name is Shanti. You've probably heard my name quite a bit this semester. I am your TA for geomorphology this semester, and I'm going to be giving a little mini lecture on OSL, which is optically stimulated luminescence dating, just to give you kind of an idea of a little bit about this method and how it applies in geomorphology. I use this method a fair amount in my research. I actually was able to complete a little short course on it. So I do know a fair bit about it. And so I'm going to be walking you guys through some of the applications that I've used for OSL in my research, as well as giving you kind of an overview of this method and how it can apply in geomorphology. Who am I? I guess I just said that, but in case this is the first time you've ever seen my face, I am a PhD candidate working with Andy. I am actually focusing my research on glacial and fluvial processes and paraglacial landscape evolution. And these are just some pictures of me in my various research pursuits. Most recently, I was able to do some research with Andy in Argentina, where we actually were able to work on the Southern Patagonian ice field, which was pretty cool. And unfortunately got cut a bit short by COVID, but you know, that's just how this year goes for everyone, unfortunately. So let's talk a little bit about OSL and some of the applications of it. So before we do that, let's just pretend that we are some field geomorphologists and we have gone out in the field and we are standing at this outcrop. This is actually a photo of an outcrop that Andy and Phil Larson at Mankato State have done a fair amount of work on. And it's basically this really beautiful sort of wall in this quarry. And so as we look at it a bit closer, we can see that we've got a lot of very, interesting layers going on here. So we can see sort of, this very nice sort of sandy layer, definitely some sort of break in between these two layers to sort of have some sort of different looking sands and gravels up here. And then also there's definitely some sort of different thing going on down on the bottom. We know that this field site is in Minnesota. So this is the Minnesota River. Over here we have Minneapolis-St. Paul. And this field site is actually the Cambria pit. So we know that it's on the Minnesota River. There's also been some amount of sampling that's been done on some of these other pits, but we know that probably some of these sediments we're looking at is possibly connected to Minnesota's sort of past and some of the work that's been happening on the Minnesota River and some of the sort of geologic story there. So as we look closer at this outcrop with Andy for scale, we begin to see that there are some ways that we can possibly break it up. So we, as I mentioned, sort of notice that there's definitely, lots of junk on the bottom. So that's not really anything that we can do much with because it's not really in place. As geologists, if something is not in place or in situ, it's not really something that we can work with. However, if we look kind of above that, we can see that there's kind of this interesting darker deposit. And sort of the preliminary interpretation of this deposit, thanks to Phil and Andy, is possible that this is actually from an oxbow lake. They think that because it's definitely looking like it's very organic rich and just sort of the types of sediments, very fine grains that they see there. They think it's that, they're not entirely sure. Above that, we see there's definitely sand, climbing ripples, migrating dunes. These are all bed forms, things that you learn about in sedimentology, but definitely sort of some more fine grained sandy stuff on top of this very organic stuff. And then on the top, it's definitely quite a bit coarser, a lot higher energy, and we sort of see sands and pebbles. So we kind of look at this, we see that there's sort of these 4 different units. We don't really know much about how they fit into the larger story of Minnesota's geology, and we don't really know how they relate to each other. Were these deposited one after another, or is it possible that some of these, were exposed at the surface for a long time? There used to be a lot of it, it got eroded down, and then the unit on top of it was deposited. We don't know. And we also don't know generally, like what was the river doing? If the river was, kind of able to make migrating sand dunes, that's a very different type of river than one that has clasts and sort of bigger sediment in it. And so knowing when that is also kind of really important to begin to reconstruct, what happened here? How were we able to form this sort of sequence of packages? And so those are some of our guiding questions that we have, thinking a little bit more about what we know about Minnesota's glacial history. You may or may not have heard much about this, but there was a very large glacial lake called Lake Agassiz that was formed by the Laurentide ice sheet, which covered large parts of North America. And this lake, we know from other sort of geomorphic studies, had a really large drainage event that is actually thought to be responsible for the carving of the Minnesota River Valley. And so kind of how can we link some of these sediments that we're looking at in this outcrop with this event that we know happened in, in the past in Minnesota? So, what was the impact of that on this sequence? And, can we actually see evidence of that in this sequence? And then also, we know approximately when that happened. We know it was around 14,000 years ago. Are these sediments younger than that? Can we use these sediments to then possibly begin to understand how the landscape has evolved, or, what happened, before, during, and after this event that we know about? Because we know that this outcrop is right next to the Minnesota River, so presumably it records something related to Glacial Lake Agassiz and the flood, but we don't know what. And so that's where optically stimulated luminescence can come in. And so our big question that we're trying to answer that will really help us sort of factor this outcrop into the research that we're trying to do is, when were these sediments deposited and buried? What is the age of them? If we're able to figure out the age, then we can say, oh, well, this really gravelly unit on the top has this age. So that, if it's this old and it's the same age as when Glacial Lake Agassiz was around, then that could tell us something versus if there was a lake. And so this is the big question. And so that's where optically stimulated luminescence dating comes in. And so you might be asking, what is optically stimulated luminescence? So in geomorphology and just in earth science in general, there's a number of different geochronological techniques or ways that we can figure out how old samples are. And so what optically stimulated luminescence dating is basically you're using light, optical, that's the optical part, you're using light to stimulate mineral grains to determine the time since the grain was last exposed to sunlight. And so this is a really cool technique, and you basically can take these grains, stimulate them with light, measure what comes off of them, and say, okay, this grain was buried around this time. And so that's really useful in sort of surface processes environments, because we can say a river was flowing here, deposited this grain, and it got buried at this time. Or this grain was picked up by a sand dune in the wind and blown around and then deposited and subsequently buried at this time. So it's really useful for surface processes. There's many types of sort of luminescence techniques. So this is optically stimulated luminescence, so it uses light to sort of get at this signal of how long since a grain has been exposed to sunlight. But there's also a technique called thermoluminescence, which actually stimulates grains with heat. But that's less common today because it actually can destroy your sample. And the really great thing about optically stimulated luminescence is you actually are able to kind of fine tune and keep working with your grain as you keep re-exposing it to light, which I'll talk about in a little bit. So a little bit more about just the basics of optically stimulated luminescence. The main application of it and the main mineral that it's used with is quartz. Quartz is fairly simple. It's just got silica and silicon and oxygen. So it's fairly simple tetrahedral shape for all those that took mineralogy. But it's also can be used, similar method, but slightly different with feldspars. But that is actually called IRSL, infrared stimulated luminescence, because you have to use slightly different wavelengths. Feldspars are useful, and definitely in situations and settings where you don't have very much quartz available, it's definitely a great method to have. But just like feldspars, feldspars are a lot more complicated. The method itself is a lot more complicated because we have to take into account sort of the more complicated crystal structure of feldspars versus quartz, which is a fairly simple grain. So how does OSL work? Like, what is it? I just talked a little bit about how you optically stimulate grains, but what does that actually look like? So quartz and feldspar grains are not perfect. They are, beat up. They've been possibly made slightly imperfect, or they've, been eroded and weathered for long periods of times. And so as they sort of get broken down and kind of beat up and kind of grungy a little bit, they can get imperfections. And these imperfections actually are capable of trapping electrons. So if you think of, like a perfect grain has a very smooth surface, but over time it's kind of eroded and chipped and beat up by just erosional processes, it'll get kind of pits and grooves in it. And these sort of like imperfections and sort of physical, breakages in the crystal grains themselves actually can become nice little homes for electrons. And so we call these traps, and they're imperfections in the crystal lattice. And basically what we have is we have our little grain hanging out in the substrate. It's buried under the surface, and just around it naturally, you're going to see radioactive elements decaying. And as these decay, they're just going to come up and get trapped in the electron traps. And so this is a diagram here, black and white, kind of old school diagram of this process, but it's showing, we have cosmic radiation. So the types of radioactive elements that I was just describing, we can have radiation coming in from the environment, but we also have, just stuff normally in the soil. And this sort of, beta alpha decay just from radioactive elements is sort of going through the soil. And as it kind of hits a plagioclase grain, it can become stuck if there's imperfections, or if it hits a quartz grain, it'll become stuck. And so these sort of allow these quartz grains to sort of build up this radioactive energy and these radioactive electrons over time. And so we call these electron traps. So I just mentioned this before, these imperfections in these quartz and feldspar grains that trap electrons are called electron traps. So a little bit more about how it works. So we have these grains that are able to trap bunches and bunches of electrons. Sort of think of it as like a bunch of grapes. So over time, it's sort of accumulating grapes. So we have electrons sort of hanging out on this grape bunch. But once we actually stimulate that and sort of bring that grain back into light, there's so much energy that these electrons can immediately finally escape. They become stuck, but once the sunlight or once some sort of light is exposed to these grains or to these electrons, they can immediately leave. And so think of it as our bunch of grapes. Once it sees sunlight, all the grapes fall off just because there's enough energy. And this process where electrons can be released is called bleaching. And so what we do in OSL is we kind of take advantage of this fact. So we have the fact that sort of these electrons are accumulating over time, and once they're stimulated to light, they can be sort of immediately released. And so we sort of exploit the fact that we can maybe possibly figure out the rate at which they're accumulating onto our electron or onto our crystal. So we can say, we know approximately the rate that they're going to be adding one grape at a time. And then based on that, and sort of once we expose it to light, if we measure how many grapes there are, then that will really help us then begin to see how long our grain has been buried. So we stimulate it with specific wavelengths of light to release these trapped electrons, and we are able to estimate the time since the sediment was last exposed to light. And so before I go into that, I'll just sort of talk a little bit about this diagram. And another sort of way, I know I just use the grape analogy, but another really interesting and kind of helpful way to think about this is sort of like charging a battery. So we have our grain sort of moving through the, environment. It's seeing sunlight. So let's imagine this is a little sand grain that's picked up by wind, and it's blown around and it's deposited. But as it's being blown around, it's being exposed to sunlight. So all the trapped electrons that are sort of stuck on it are released as it's sort of moved before it's deposited. Then it's deposited and it's buried. So when it's deposited, it's empty. So it's sort of like an empty battery, and it's buried. And then as it's hanging out underneath the surface of our imaginary system, there's sort of radiation coming in from various radioactive elements that are just naturally in the soil. And those are going to start recharging this battery again and filling it up and giving it more electrons until it's exposed to light and sort of transported again, where it will then begin to drain. So it's sort of like a rechargeable battery. However, one kind of important point in this that we'll talk a bit more about in a little bit is that sometimes this grain does not reset completely. And this is actually where we have a situation like partial bleaching. And so partial bleaching is where we have basically our grain was not transported far enough. We only got to sort of this point in the battery where it's half full. And so then we have an issue where it's not starting from the beginning, where it's an empty battery. We're starting from a half full battery. And so we have to kind of know that that's an option. And there are ways that we have to sort of factor this in as we begin to try and use this to date our sample. And this is very common in glacial and high turbidity environments where you know, maybe the grain might not see very much sunlight. Because if you think about, I don't know if you've ever been to a glacial place, but they have this very distinctive, lovely light blue water that you can see in glacial environments, like very, very bright, bright blue. And that's because there's so many fine grained sediments that are suspended in this water from the glacial erosion, and sort of, you know, just have been broken down. And that's really beautiful and makes great color. But if you're a sand grain trying to see sunlight, it can often be very hard just because there's so much water naturally suspended in the sediment. And so this is a very sort of basic plot that of just what I just talked about. So we have sort of our sediment being deposited here. It's sort of building it up over time, and then it's exposed to light, that's released, and sort of becomes zero again. And so a little bit about how we actually use this for the age calculation. So I just talked about how we kind of have two factors here. So we have the natural radiation kind of coming from the surrounding environment. So as our little empty battery is hanging out under the soil, it's going to be getting natural radiation from just natural radioactive breakdown around it. And so this is what we call the dose rate. So the flux of radiation from the surrounding environment. So the amount of radiation coming into our little empty battery, empty crystal from the environment is called our dose rate. And then the equivalent dose, so once we have our sort of fully charged up battery, we take it and we expose it to light and we see how much charge comes out. So we can say, okay, like it's sort of, then going back to my grape analogy, if we have our little thing, we see, okay, how many grapes came off when we stimulated it, like how many electrons came off. And so this is the intensity of the OSL signal, the amount of electrons that we're able to build up in our like hypothetical little grain. And that's what we call the equivalent dose. And so the way that we're able to possibly, or to begin to figure out the age for these types of samples is we take the equivalent dose, the amount of light that came off of our sample, versus the rate, the dose rate, the sort of amount of natural radiation coming into our sample from the environment, and we sort of divide those, and then we're able to figure out an age. We're able to say, okay, we know the accumulation rate, we know how much natural radiation is coming in, and we know how much radiation we got off, and that will tell us the age of our sample, or how long since it's been last exposed to light. And so that's what I was just walking us through. So the intensity, the equivalent dose, or the intensity of light when the sample was exposed to a known amount of simulation, that's what we're doing in the lab, versus how much radiation is coming into it from the surrounding environment. And so this is just showing how the units work out. So the intensity of light is measured, the units that they use in OSL is called grays, or GY. So the amount of light coming off is grays, and then we know the rate going in is grays per kiloyear. Divide those, we get kiloyears. So back to our hypothetical, or actually not so hypothetical, actual application of OSL that I was able to help with. We have some samples that we took. So this is again looking at that face we were just looking at, and sort of thinking, or sort of defining some of the layers that we saw. And so these are two samples that I actually was able to help analyze at a lab in Utah. I worked at Utah State University for a few weeks and ran these samples. So we have one sample that we took here from sort of this interesting sandy unit, finer grain with some beds. And then we also took a sample below in sort of some sort of gravel bed thing below sort of this possible oxbow. So we have samples above and below, and by figuring out the age of these samples, we can then sort of not only get bracketing ages for this possible lake deposit, we can also then say, oh, well, the river we know was kind of sand dominated, had this type of behavior pattern at this time, once we know the age of this, and then we know it was more gravelly once we know the age of our lower sample here. And here's just some more close-ups. This is a picture of Phil, who works at Mankato State. This is just some more close-up samples. So the way that we sample for OSL is actually a very fun thing. I won't go into super details of it, but basically, not surprisingly, you want your sample to stay in the dark. So the way that we do this is we actually pound in these metal tubes. I have a picture of it on the next slide, but one of the common ways we do it is we pound a metal tube into our little outcrop face. And so if you get it in deep enough, the samples are still in the dark. And so you take that metal tube, and you have your sample that's in the dark, and then you also take a separate sample from the surrounding material, and that's what we use to sort of figure out the surrounding environment, what actual radioactive elements are there. That one doesn't need to be kept in the dark as much because we don't care about the actual luminescence. But yeah, these are just some close-ups. I'll show you some more photos of our actual sampling, our actual analysis. So this was me working in the lab in Utah State. So I just mentioned we take some samples from the surrounding environment. This is what we use for the dose rate. So figuring out how much radiation is coming from the natural environment. These don't matter to be kept in the dark because we're literally just going to figure out what elements are there and what's radioactive. So this was me sorting and sort of doing some splitting of these samples because we only need like a very small bag of it. So I had to divide it up, you know, based off of the grain size. So you can see I have a cup of very large grains, more medium grains and finer grains. So this I got to do outside. And this is an example of the stuff that we then use for the equivalent dose that has to be kept in the dark. And so this is one of these metal tubes. Super fun to fly with, TSA. Gets very confused when you have a bag full of metal tubes. But this is a sample that needs to be kept in the dark. And so here is a photo of the OSL lab that I got to work in Utah State before it was an actual lab. Not surprisingly, they don't let you take photos in the actual lab because any sort of light, even the light from a phone screen, can destroy these samples, like because they'll stimulate them and you'll lose your signal. So it's actually not quite as bright as this. They have these fun orange lights that you get to work in. It's all in the dark. So yeah, this is just a photo of it. I obviously don't have any photos of the actual analysis because it's in the dark. But yeah, you do a lot of fun processing in the dark. I'm happy to talk more about some of these steps. But you're able to work with these samples in the dark, put them in an instrument that then measures, stimulates them with light and measures how much radiation comes off, does some fine tuning with that, and that's how you're able to then get your equivalent dose, which you compare to your dose rate. So here's some data from some of the work that I did on these samples. We don't have to worry too much about the actual nitty-gritty of this for this lecture, but I just thought I would show you some of the cool plots I got. So this in the middle here is a dose response curve. So this is basically showing how the sample is exposing or responding to stimulation. So right here is when they expose it to light, and this is sort of the bright peak of reaction. All the electrons are released, and then it very quickly decays. So this was sort of our decay of that. And then this was showing, so you test it at different radiation levels. So we sort of take it here. This is sort of our initial reaction, and then you sort of keep exposing it, keep fine tuning it. And so you're able to make this other sort of response curve. And then this is more about the calculating of the age. You don't have to worry about it too much. And then just a little bit about how I actually sort of did some of this lab stuff. It actually, you have to sieve it. So you have to go through and get a certain size fraction. And so I had grains between 150 and 250 microns. So it's fairly coarse. And I actually, for this specific sample, analyzed 5 small aliquots. So 5 small little piles of sediment. But I actually only was able to use 2 in my age calculation because of just a number of factors that came up in the process. You know, they didn't have enough signal, or they might have been contaminated, things like that. And so that's actually fairly common in this technique. So that's why you have to run so many samples. Like I only did 5 when I was there, but you know, they'll run hundreds just to get a date on one specific sample, just because there's so many things that you need to fine tune. And so when I analyzed this, I got an age of 46.8 plus or minus 4,000 years. And that was super off from what we expected, because we knew that these samples were collected, you know, from the Minnesota River area, and we generally kind of were expecting them in about the 14,000 year age range. And that was based off of what we already knew about Glacial Lake Agassiz and when, you know, the sort of floodwaters from that were moving through the area. So we were really surprised by how old the state was. And then we decided, you know, to do some partial bleaching, or we decided that probably partial bleaching was sort of what was going on there. And so we decided then, instead of doing small piles of sand, we were just going to individually analyze each individual grain. And so that is called single grain dating. And basically that allows us, you know, if we have a situation like partial bleaching, where we're getting, you know, things that are not fully exposed to sunlight, that can really throw off our age calculation, because that can make our sample seem older than it is. And because we knew this was a glacial setting, we thought that was probably what was going on. And so that's why we decided to, instead of doing small piles, do each individual grain. And so a little bit about this, a little more of the detail. So Yeah, partial bleaching can give ages older than the sample actually is, common in glacial settings. And so this is sort of highlighting the importance of knowing the stratigraphy, where you are, your setting, and the approximate age. Because, you know, it doesn't really matter if the sample is actually that age. If you analyze each individual grain, you should get the same thing. But if you have a situation where your age is way older than you think it is, that's where single grain can be really helpful. So we actually did that. So this was, when I was there, I did small aliquot, and I got, you know, about 47,000 years old. We knew that was kind of old. So then after I left, the lab went back and did single grain, and based off of an average, or sort of looking at all of the dates and sort of seeing what made the most sense and where actually most of the grains were without some of these super old ones to sort of draw the age back, we then got an age of about 13,000 years. And that is a lot more in line with what we were expecting. And that is actually the age that we went with to sort of finalize going forward. So this just highlights the importance of knowing your setting, and also the availability of sort of different ways of tweaking OSL to make it work best for your sample, and kind of how you have to sort of work through and think about the process as you're sort of trying to analyze your samples. So going back to our field setting, these were sort of the two final dates that we got for these samples. So we got, this was the one I was just talking about, so about 14,000 years old. And then below this lake, we got this much older age, about 53,000 years old, which was a lot older than we expected. But after we did single grain, we still saw that the majority of grains were this age. So this was the final age that we went with. And so what are the implications for this? You know, now we've been able to apply geochronology to our field area. What are the implications? Well, we think, you know, maybe this is an erosional surface. Maybe there was a situation where, you know, this was able to erode over a long period of time, and that's why it kind of cut down and got so much older, and then there was infilling on top. That could be a situation that we have here, and that kind of isn't one of the sort of stories that we're now able to pull out now that we know the age. We do sort of see just stratigraphically looking at the outcrop that there's sort of signs of rapid infilling. So we know sort of starting around like up here, it really filled in fast, so we know kind of generally that that rapid infilling started around 13.9 thousand years ago, which generally makes sense with kind of what we're thinking for the area. And so maybe one of our other possible like situations that we can now guess at from our dates is, you know, we sort of had possibly a situation where we cut down to create a bedrock platform, deposited some gravels. So that's where this kind of came in. We had a lake there, and then we had a rapid deposition of deposit of material on top of that, starting around the sort of 14,000 year thing. So more information is sort of needed to get a better understanding of what could be going on. More data points are needed. Obviously, you can't use 2 data points to figure out a whole chronology of the field area, but these field areas, or these 2 samples, do give us really good insights into, you know, approximately, you know, at this time period, this is how this particular area was behaving. At this time period, we know this. And so this is giving us a new understanding of this river behavior and what was going on in the system around the time of Glacial Lake Agassiz. And so that's why geochronology is such a powerful tool, because it really allows us to put numbers on some of these theories that we might have had. Like, we knew generally that, you know, sandy bedded rivers behaved a certain way, but now we can line that up specifically with the chronology of the past because of the use of OSL in this setting. So just to kind of do a quick little wrap up here. So OSL, optically stimulated luminescence, basically it is using light to stimulate quartz and or feldspar grains to determine when a grain was last exposed to light. And this is really useful for depositional history, really useful at trying to figure out, you know, when certain surface processes were happening in a certain area. It's applicable in a lot of different geomorphic settings. I talked a lot about fluvial and glacial settings, but I also mentioned a little bit aeolian settings. Aeolian's great because obviously it's moving through the air, so you really don't have to worry about grains not being exposed to light because there's lots of sunlight up there. But it's definitely applicable in a lot of different sort of, you know, hill slope, that types of settings as well, in surface processes. The analysis can be complex. You have to take into account your depositional environment. You have to take into account what you know about when you sampled, things like that, to sort of fine tune your analysis and maybe use slightly different methods based off of what you know. So it can be complex, but in the end, you are able to receive, pretty reliable dates and really useful dates that, allow you to understand kind of what the process was doing and what was going on. And it's just one of many geochronological tools available to geomorphologists today. And it's a pretty cool tool. And it's one that I'm, really interested in and really excited to be using in my research. And hopefully this was kind of interesting to you and kind of gives you some more insight, as you're reading your next paper on geochronology. Maybe this will pop up, you'll know a little more. But yeah, that's all I've got for you today. If you have any questions, I'm available over email. And yeah, I hope you enjoyed seeing my face for a change. So thanks. Bye.